morning and good afternoon, everyone, for our friends in Japan. My lecture will be about control and estimation challenges in mobile manipulators applied in the field. Just a brief introduction of my group. We work on mobile manipulators, on vision-based sensors, on optimal estimation and control problems, teleoperation, and robot design aspects. Currently, our research is focusing more on the dynamics and motion control of mobile manipulators with applications to fruit harvesting and weed removal, and also the design of operational space controllers and combining this with deep learning for manipulation, mobile manipulation tasks. So why mobile manipulation? I think it's the next step, because if you consider the evolution of robotics, this is a chart that was published by PricewaterhouseCoopers a few years ago in 2017, showing the evolution of robotics. And you can see that in the 70s and the 80s, most of the research focused on arms, on robotic arms. And then we have the 90s and the early 2000s, which were focusing on mobile robots. So now we have vacuum cleaners, semi-autonomous cars, which have reached the market. And the next step is to have platforms that can move, but also interact with objects. So we are still working on that. Even if there are humanoids are very expensive robots and are very far from being applicable, at least in the short term, for commercial purposes. So we are looking to combine the advantages that the arm gives you with the mobility of the base to solve some concrete problems to our local reality. Agriculture and mining are two very important industries here in Chile. So we wanted to, a few years ago, build a robot that could harvest, especially table grapes and some wine grapes that are, there are some harvesting machines for wine grapes that beat the plant, and it doesn't matter because then they will squeeze the grapes and turn them into juice. But if you want to have these premium quality wines or table grapes, you cannot beat the plant. You have to pick the fruits by hand. But there, as was mentioned by Professor Noguchi, a shortage of labor costs are also rising, and people don't want to work anymore in the fields. It's tedious, it's repetitive, but it's also harder compared to indoor robotics. So we wanted to build these robots to harvest, and the first problem is, well, where is exactly the fruit? And we then started working on grape bunch detection. And we did a work which was showing high rates of success and accuracy in the detection, which was published in Computers and Electronics in Agriculture. So we were able to detect different varieties of green grapes and also red grapes. And we also were able not only to classify pixels, which is what most people do for yield estimation, but also to find if there were overlapping grape bunches. So our detection accuracy was above 95.5%, depending also on the variety, because sometimes white grapes are harder to detect because they have smaller contrast with respect to leaves. So this in part was a starting point to work on mobile applications, which have to interact with objects. This is an example also of a problem that was posed to us a few years ago. The national airline company wanted to repaint airplanes, and they have to sand the airplane completely. They wanted to use robots, but the conclusion was that they cannot use regular robotic arms that are used in factories because the arms do not have the reach necessary to cover large surfaces. So they need a mobile base. And as I was mentioning, in agriculture, not only for inspection, but also for handling the fruits or handling dangerous materials. Obviously, in indoor applications, there are many possibilities for mobile manipulators. And as I was mentioning, also in mining and agricultural situations. Not only because you want to automate the process, but also because you want to reduce the energy consumption. In this video, this is a video of the Opportunity rover in Mars, and you can see that the robot is sleeping. So that means there is an energy consumption that is not producing adequate motion, translational motion. And the same thing happens with machines in the field. I'll show you another video of our experiments. And this is our machine. And you can see there that the wheel is sleeping, and that's fuel that is consumed doing nothing, basically. And part of our work was to detect those situations when the robot is trying to pick up soil or material. So the first part was to develop very physically accurate models that could allow us to simulate and replicate what was happening in the field. And by very accurate, I mean that even the wheel-ground interaction had to be modeled, because the wheel-ground interaction propagates forces to the arm that have to be compensated if one wants to keep the arm stable. Or you can have situations in which some of the wheels are not touching the ground because of the unevenness of the terrain. So you have skidding. And concerning the perturbations, you can see here that these machines that are semi-autonomous, they are teleoperated, are sometimes dropping material. The objective is to maximize the load. So the operator will try to fill the bucket to its maximum capacity, but as it moves and vibrates, it loses material. So part of our work was to decouple the motion of the arm and have the arm as stable as possible. And also part of our objective was to estimate online the parameters, the inertial parameters of the machine, because in that way we can measure the transported load or even the friction in the wheel axles, which give us some information about the wear of the machine. So there are a lot of technical details, and we will not have the time to go into the details. But as I was mentioning, there are different applications in agriculture for monitoring fertilization, phenotyping. There is an increase in world population and also a decrease in arable land, and also a lack or shortage of field workers. And climate change is another factor, important factor for introducing more automation into agriculture and being more efficient in the use of resources. So in this graph, we have this blue line, which represents the arable land per capita. So it has been decreasing almost by 50% since the 60s. So now per person, less than 0.2 hectares are being used to produce what we consume. On the other hand, the population has been increasing, but now we are around 7 billion people, and it's expected to continue to grow to 9 billion by 2050. So, as I was mentioning, this scenario may seem a little bit pessimistic, but on the other hand, if one thinks that the land that we are using to produce what we demand has decreased, and we are still able to satisfy the demand, that means that it's the introduction of phytosanitary products, fertilizers, and different agrochemicals, and the use of technologies that have allowed this increase in efficiency. But there is room still for higher efficiency. This graph shows different fruits and the production, the value of the production at the aggregated world level. And we can see that grapes is a very high value crop. And that's one of the reasons why we were focusing on grapes. And then in the context of mining, there are other aspects which are related to safety and also productivity. And also in Chile, we have 30% of the copper that is produced in the world. So in both cases, both in agriculture and mining, there is an objective, an economical objective, which is to increase yield and efficiency. Sustainability objectives related to reducing water consumption and the CO2 footprint, and also technical objectives which are related to how do we manipulate things in environments that are not structured and that are less deterministic than indoor environments, and also aspects related to safety. So, well, concerning efficiency, one of the first things that we wanted to do was how do we estimate the mass that is being carried? And one could think the problem in simple terms as a problem of, well, let's measure the force or the traction force and divide it by the acceleration, and we have the mass. Obviously, the problem is a lot more difficult because the machine is not moving in a line. It has a pretty 3D motion. There is noise in the sensors, and sometimes the acceleration will be very small, especially when it's starting. So we cannot divide F by A that in such a simple way. But one can implement different strategies, filters, to estimate the mass and other dynamic parameters in an accurate way. Once we have the mass, we can work on improving the fuel efficiency and reducing the wheel slippage. And also finding optimal trajectories, which are the trajectories that minimize the energy consumption, not only in terms of finding the smallest distance, but especially in the field, in some agricultural fields where you can have mud, there are some areas that one could avoid if you know what are the terramechanical parameters and what are the traction characteristics of the terrain, so, and the slope. So that was also part of our work, and things that I mentioned about perception and how do we improve teleoperation using virtual reality, etc. And the part of the research is also important because one needs to improve maneuverability and also train future engineers that will be capable of developing new algorithms and integrating this new technology. And well, this is a summary of our platform. We have integrated LiDARs, the teleoperation system, the GPS and inertial measurement units that we developed in our lab. And in 2014, we started with virtual reality teleoperation tests to see if we could improve the teleoperation with respect to the traditional way of looking at a 2D screen. So we developed a replica of the environment, which we can see also from a third-person point of view. And we compared how difficult it was to move the machine compared to the traditional 2D view, as I mentioned. Then we installed the torque sensors in the wheels and developed some optimal path planning strategies, considering the forces and the energy that was being consumed. I'll show a small video. So the strategy of how do we optimally harvest fruits depending on the maturity of the fruit and also the traversability costs of the terrain. So we were employing these rapidly, randomly exploring trees to develop an initial route, but also considering the mechanical aspects you saw in this image, that there are certain areas which are darker blue, and those have a higher traversing cost. So in the end, the optimal route or the robot is rerouted through the blue line. And I can show you some other videos of how the process works. So if there are different points that are defined by the user that have to be harvested, the robot picks the optimal routes, minimizing its energy consumption. So if there are more points, then the robot adds those points to its harvesting plan and optimizes the route. I'll show next. Okay, so I already showed the videos that were supposed to go here, but I had some problems with an update of the Flash player and my presentation software. So unfortunately, I could not have those embedded, but I already showed those videos. So part of the challenge was, as I was mentioning, to develop this accurate model in which the forces of the terrain wheel terrain interaction would be propagated to the arm. And this was done using the spatial vector algebra formalism. So this acceleration of the base is actually a 6-dimensional vector, which has the 3 translational components and the 3 rotational components. And these inertia matrices are 6x6 matrices. And these force vectors are also 6-dimensional vectors. So the notation is very compact. It resembles the scalar representation. But one advantage of using the spatial vector algebra formalism is that it simplifies the way one can introduce these external forces. So this is probably the main difference with respect to the traditional models that one would find in robotics textbooks, in which usually it's assumed that the floor is flat. So there are no forces being propagated to the arm. And this was important, as I was mentioning, to optimize the path of the robot, because if you want to optimize the path from an energy point of view, you need to know the dynamics. The kinematics alone, it's not enough. So this is how this kind of dynamic motion planning would work. We would start with a graphical path, or if we call it that way, which is not considered the dynamics, but then on top of that path, we have to refine the path considering the dynamics. So when you consider the dynamics, you can see that the blue line is not following exactly the black line that was found just by polygonal approximation. So on the right graphs, for different situations, one in which there is a tight tunnel or passage, or in the lower right image where you have different possibilities to reach from one point to the other, because there are two possible paths, the system not only minimizes the distance, but also smoothens the path, considering what the machine can actually do in terms of its turning radius, accelerations, limits, etc. So these are some of the aspects concerning the strategy. So instead of just joining points with straight lines as different only kinematic-based algorithms do, in this one, when the system approaches one waypoint in the trajectory, then it starts finding a smooth arc or trajectory that connects the points. And there is a radius parameter for this that minimizes the energy and smoothens the path. So concerning the wheel-ground interaction, obviously we had to model also the motion of the arm, considering the hydraulic actuators. One of the lessons we learned is that because of the response time of the actuators, it's not so simple to cancel high frequency disturbances. So the future machines that want to cancel those disturbances will have to have different actuators or a separate power plant, because in the case of our machine, the engine is driving a hydrostatic pump that feeds the wheels and also the arm. So part of the power of this pump is being consumed by the wheels. And when you want to compensate the arms, the wheels are sometimes absorbing the hydraulic energy, and you cannot respond fast enough in some situations. I'll show you a video of, let me see. So this is in slow motion, but what we were doing with H-infinity control techniques was to cancel the disturbance of this bump. And also in the case of ramps, we could compensate the change in slope, keeping the bucket level. So in order to achieve this, our strategy had a part in the controller which would use the H-infinity tune control with also a feed-forward component. And the feed-forward component can be obtained either from the inclination sensors, or if one has a LiDAR, one can look at the terrain ahead and see if there is a change in slope and start feed-forwarding this disturbance. So I will not, because of time, go into the mathematical details of the H-infinity controller formulation, but just show that without any control, you see the orange line. This is a change in the slope of the terrain of 5 degrees. And with a PID controller, one can compensate a little bit the disturbance with this pink or magenta line. But if one uses the H-infinity controller with the feed forward, which is the graph on the right, is the one that practically cancels the disturbance. With the H-infinity controller without the feed forward, the controller responds, but there is a period in which the disturbance is not fully cancelled. And we also, in the left graph, we also try the adaptive disturbance rejection control strategy, which has become popular recently. And it also does well well at low frequency or low speeds, but at higher speeds, the H infinity controller is slightly better. So we were able to achieve significant reductions of about 80%, 86% in the disturbance at low speeds, and not so much at higher speeds for the case of the ramp. And the bump are more difficult because they produce high frequency vibrations, but we were also able to reduce at least 24% the disturbances. With this, what we are seeking in the end is to minimize the loss of material that falls from the bucket. Okay. So I already mentioned these results, and the last problem was one of the problems that I mentioned first, which is how much mass are we transporting, and also where is the center of mass, and which is the rotational inertia, and additionally the viscous friction parameters. And why is this important? Because when you are trying to manage your operation, you want to know if you really have moved the amount of material that you think that you have moved. So even if there are some industrial scales that can be placed, these are expensive. They need continuous recalibration because they use strain gauges, and they do not give you information about viscous friction. So once we have the model, we can formulate a physical model that takes as input the force that we can measure and the resulting acceleration and velocities, and using that information, estimate the vector of parameters, which are the mass, the location of the center of mass, C super P, the inertia matrix, and the viscous frictions, the main viscous frictions. And well, as I was mentioning, we are using this spatial vector algebra formalism. So our velocity vector is actually a 6-dimensional vector that has the rotational component, the 3D rotational component, and the 3D translational component. The same thing for the acceleration. Then one can formulate the equations of motion for the base, and rearranging the terms. This looks a little bit ugly, but after doing the math, one can establish an equation in which the force vector is equal to this thing in the right side, which has the angular accelerations and angular velocities. And in the end, the problem can be separated as a linear problem with respect to the parameters. So one could use ordinary least squares to estimate the parameters if one measures the accelerations, velocities. The question was, can we do better than just using ordinary least squares and doing batch estimations? So we implemented an extended Kalman filter, and we also introduced something which we call the mutual information criterion, which basically tells us if there is any relation between the acceleration that we are observing and the force that we are applying, because we know due to the physics that there is a dependence. So they are not independent variables. So using this mutual information criterion, we were able to measure this degree of dependence. And when we detect that the measured acceleration and the force are sort of independent because the level of noise in either of two is too high, we discard those measurements from the estimation process. And in that way, we improved the estimates because we're ignoring measurements that we could say are bad or noisy. So just to finish with this presentation, we developed different excitation trajectories, straight lines, rotations in place, or S-shaped maneuvers. These are the formulas for the mutual independence criterion. and also an extended Kalman filter in which the filter was extended with a vector of parameters. So the first part of this equation, the process equation, is the motion dynamics, which we already saw. And the second part, this x sub p, contains the vector of parameters. And we model that as part of the process dynamics. So the parameters are not constant, especially the mass and the center of mass. And we compare the different estimation approaches. And we, both in simulation, we have the different trajectories. These are for the mass of the parameters. We can see the red one is the recursive least squares, and the blue dotted one is the extended Kalman filter. And then we also implemented the total least squares and the feasible generalized least squares. And both in simulation and in the experiments, we were able to have converging estimates in the first place, which was something important. The worst one was the total least squares. And the extended Kalman filter and the recursive least squares were the best ones for estimating changes in the load. In this case, the recursive least squares looks a little bit better. But if one compares the case of estimating the rotational inertia, the extended Kalman filter was better. So in the end, considering the different parameters that one wants to estimate, the overall error of the extended Kalman filter was a little bit smaller than what we could achieve with the recursive least squares. So this is part of what we learned and developed for parameter estimations. The problem with total least squares is that it diverges when we wanted to estimate, for example, the location of the center of mass. So that was probably the worst approach. And we can estimate the weight of the machine with errors that are below 1% of the total mass of the machine. And also the inertia parameters, the rotational inertia parameters with errors that are below 4.3%. Estimating the center of mass is a little bit more difficult because of the skidding of the machine. The mutual information criterion was very important, and I already mentioned that the extended Kalman filter was slightly better than the other approaches. So thank you very much. Domo arigatou gozaimashita.